Okay, we're going to continue on here. Chapter 14, part one. And we're talking about obviously pH. Uh, and we got into kind of the pH of a weak acid at the end. And remember, because it's a weak acid, it will actually set up an equilibrium. And because it does set up an equilibrium, I'll just use A there, my generic. We can write an equilibrium expression for it, which is just like any other equilibrium expression, H plus A minus in this case over HA, if HA is an acid, a weak acid. This again is what is known as the Ka value. And the Ka value is an equilibrium constant for weak acids. As we talked about last time, strong acids, because they are strong electrolytes, will not really set up an equilibrium. So it's a one-way street. Also, like we talked about last time, because of that, for strong acids, you basically know the H plus concentration from it because it will completely dissociate and you can calculate the pH. But with weak acids, because they do set up this equilibrium, you do need to do an ice table here to figure out the pH. And really, the purpose of the ice table is really to figure out what is the H plus concentration in that solution at equilibrium. Once you do that, in most cases, I would say when you solve for X, that's going to be the H plus concentration in most cases. You'll be able to go right into your pH equation after you do the ice table in this particular case. Remember, there's really only about six strong acids. Again, hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic, and hydroiodic acid. We do not typically see a Ka value for a strong acid because it doesn't set up the equilibrium. So as we talked about before, if you definitely see a Ka value associated with an acid, you definitely know it's going to be a weak acid. And again, you want to take this sort of ice table approach. Any questions on that stuff there? All right, we did an example with HF, I think, last time, and it was 0.5 molar, I think, HF there. And it had a Ka value there, 6.4 times 10 to the minus 4 was the Ka value. Now, if we actually did the exact same problem, but the concentration was a little bit different, it was 0.05 molar rather than 0.5 molar. Again, a reminder that if we go through our sort of ice table here, we would end up with 0.05, 0, and 0. Change would be minus x, plus x, and at equilibrium 0.05 minus x, x, and x. This would go into our Ka expression, which would be our products over our reactants, just like we did on the problem at the end last time. And put in our values to give us x squared divided by 0.05 minus x equals 6.4 times 10 to the minus 4. Now, on the problem that we finished at the end last time, we did an assumption and we did assume that x was equal to 0. And in this particular case, if we do the same thing, we will get 0.05 equals 6.4 times 10 to the minus 4. I'm going to multiply and then square root afterwards. And if I do that there, 6.4 to the minus 4 times 0.05 and a little square root action. That's going to give us, in this case, an x value of 0.00, call it 566. Remember, just a reminder that you should always check your assumptions. So if we do check our assumption in this particular case, we would divide it by 0.05 and times it by 100%. And in this particular case, what we would find is it's about 11%. And this would be a bad assumption. So just a reminder that not all the time will assumptions work. You do want to make sure that you check it because if not, you'd have to go back, obviously, in this case, and solve it via a quadratic in this particular example here. What is the difference between 0.5 and 0.05? It's actually the concentration is the difference. And as we'll talk about in a little bit here, the idea here is the last problem that we finished last time had a concentration of 0.5 molar, which is about 10 times more concentrated than this guy. And because of that, the assumption's okay because it was a relatively good amount of starting. Here we have a much smaller initial concentration, so when we lose that a little bit, it is more significant than it was in the previous one. I like to equate it to a pizza. If you got a whole pizza and you take a slice, it's okay. So got almost a whole pizza left, right? But if you're down to the awkward, only two slices left in the box, and you take one slice, and now you just took 50% of what was there, right? So is that even though you still took only one slice, it is a much more significant situation in the last part there where there's only two slices left, and you don't want to be the person taking the last one, I suppose. But it's much bigger. So the assumption will work in certain cases, but it definitely will not work in all cases. And sometimes the concentration that you're starting with is a big factor in whether or not your assumption will work. Any questions on that there? All right, so as we saw there, and as we did last time, we do a ice table. We really work it like any other sort of equilibrium problem here. Again, the major difference is, like I said, you usually are looking for pH in these type of questions. So you're going to want to get that H plus concentration and then put it in to get your pH. And again, you could solve it with an assumption or quadratic. Like I said last time, probably won't have too many perfect squares happening in a sort of weak acid or weak base situation. So it's going to be one of those two ways to do that. So why don't we try another one here? What is the pH of a 0.122 molar monoprotic acid who has a Ka value of 5.7 times 10 to the minus 4? If you're not sure what formula to use, you could just use this HA. It's kind of like a generic acid formula if you want. Okay, so let's take a look, see how you're doing. So once again, when we look at a problem, we have some information given to us. Real big piece of information, obviously, is we have a Ka value associated with this acid. So that automatically tells us it's a weak acid, and that should automatically trigger a ice table in your head as to the approach you should take here. So with that being said, we're just going to kind of use our generic formula here for an acid, in this case, a weak acid, and show it breaking apart into its ions. That will give us obviously a Ka sort of expression of H plus, A minus, and HA. And that's going to equal our 5.7 times 10 to the minus 4. Going into our ice table here, we got 0.1220 and 0. Change going to be minus x plus x, if I can write the x, plus x there, equals 0.122 minus x, x, and x. Question on the table there. We're going to throw that in there, and that's going to get us x squared divided by 0.122 minus x is equal to 5.7 times 10 to the minus 4. It's a small value of k, so you can assume x is equal to 0, but after our conversation we just had, you hopefully should know it is a bad assumption at about 6.8%. So we do need to go through and solve it sort of quadratic. So we're going to multiply that to the other side. And that's going to give us x squared is equal to 5.7 to the minus 4 times 0.122, 0.00006954 minus 5.7 times 10 to the minus 4x, bringing everybody to one side. Going to get us x squared plus 5.7 times 10 to the minus 4x. And that's going to be then minus, maybe do a little scientific notation here, 6.95 times 10 to a lot of zeros, 1, 2, 3, 4, 5, minus 5 here. I did not screw that up. And that's going to equal 0, and that's going to be our A, B, and C in this case. And going into here, that will get us minus 5.7 times 10 to the minus 4, plus or minus. If we do the inside of the square root, 5.7 to the minus 4 squared, minus 4 times A, which is 1, times C, which is negative 6.95 to the minus 5. That looks like inside the square root before you take it, .0002783, and then a little square root action on it. Gonna get you 0.01668 there, divided by 2 times A, which is 2. So doing the plus here, minus 5.7 to the minus 4 plus our 0.01668 divided by 2, going to give us an x value of 0.008055. Or if we do our subtraction, I feel like that's not going to be good at all because I'm going to end up with a negative number, but we'll just pop it in here, get the number, and that's going to give me a negative 0.008625. Obviously here, since we're looking for the H plus concentration and equals X, our negative value here is not going to be a good choice. That would mean that this guy here should be our X value and also our H plus concentration. That means we could go our pH is equal to minus the log of what's above there, 0.008055. So minus the log here, 0.008055. Yep. A little 209 action there. That's our pH. I'm sorry. Yes, you. What are you asking? Oh, for this one here? Oh, yeah. So it depends on your calculator. If you have a display calculator, which it looks like you do, you would hit the negative button, the log button, and then just put in 0.008055. Yeah. If you have a non-display calculator, you actually have to hit the number first and then hit the log button, then the negative and stuff. Yeah. Other questions? All right. So again, another reminder, make sure you do check those assumptions. May not always work. Yeah. All right, try another one here. What is the H plus concentration of the HCN solution with a Ka value of 6.2 times 10 to minus 10 in this case? Perhaps the right. All right, so let's take a look again. Ka value given to us, so definitely weak. So we'll do our ice table here, our HCN, which is our weak acid. We'll break apart into H plus and Cn minus. Again, that's going to give us a Ka expression of H plus times Cn minus divided by HCN, and that will equal our 6.2 times 10 to the minus 10. Putting in our initial here, 0.0100, change minus x plus x, equilibrium 0.01 minus x, x, and x. Going into our expression, that's going to give us x squared divided by 0.01 minus x equals 6.2 times 10 to the minus 10. Here we could assume x is equal to 0. That will give us x squared divided by 0.010 equals 6.2 times 10 to the minus 10. Once again, we're going to multiply followed by a square root after that. So if we do 6.2 to the minus 10 times 0.01 and then square root it, that's going to give us an x value here, excuse me, of 2.5 times 10 to the minus 6. We do want to check it again, so we're going to take that and divide it by our initial concentration, times it by 100%, and I think our check is good here. I think you're like 0.02%, so you should be good. In this case, once again, our H plus concentration does equal X. So it looks like number 2 there would be a winner in this case. And it didn't ask for it. Obviously, if we were looking for the pH at that point, we could put that into our pH equation. And that would get us the pH of the solution of about 5.60 here in terms of our pH. Any questions on that there? So hopefully you can see weak outs is pretty much just equilibrium problems with the additional step of basically figuring out the pH at the end. But everything else really just works the same as sort of normal. Any question? All right, the next thing we're going to talk about is percent ionization of an acid or even a base, really. And percent ionization or percent dissociation basically just means the percentage of it of this acid breaking apart. And really, to calculate it, we take the ionized acid concentration divided by the initial acid concentration and times it by 100. It is essentially how we do our check, basically, when we do an assumption. It's basically percent ionization is actually what you're calculating. And if it's less than 5%, it's considered not that big of a deal. If it's greater than 5%, it is. So basically, that is how we check our assumption. And that's also how you calculate percent ionization, is basically the purpose of it. Obviously, something that is a strong acid will completely ionize. You'll have 100% ionization. Obviously, with a weak acid, we get some different percent ionization that occurs. And earlier, as we talked about in terms of the concentration, you can see that as the concentration gets larger, the percent ionization gets smaller. So the kind of the bigger initial concentration you start with, that amount of ionization or H plus is going to come off in the solution is going to be relatively small. And that's why, again, those assumptions work okay when you do it. It's less than 5%. But you can see if you drop the concentration to a smaller initial concentration, you end up with a much higher percent ionization, as my pizza example. Again, you're starting with a small amount. So if you lose a little bit, it is still very significant because you only started with a really small amount, rather than if you started with a large concentration or a good initial concentration, that little bit that comes off, it's not going to be all that significant and stuff. So let's take a look at this sort of problem here together. A solution of 8 molar formic acid is 0.47% ionized. In this case, we're actually looking for what is the Ka value of this acid. One thing that we do know about this acid is, since we're looking for a Ka value, it definitely is a weak acid. So we can kind of just take our weak acid and again show it dissociating. And we can write our Ka expression for it, which, just like normal, is going to be our products over our reactants. And in this case, that is kind of what we're looking for. So if we were to sort of just roll through a normal ice table, which is normally what we would do in a weak acid situation, we would go with 8 molar here. This would be 0 and 0. Our change would be minus x plus x plus x. That means at equilibrium, 8 minus x, x, and x. Now, this is our normal sort of ice table that we would do with a weak acid. Normally, at this point, we would go put it into our Ka expression and solve for x. Problem is, obviously, we're looking for the Ka value in this case, so we can't obviously do that. So we have obviously used this piece of information. There is one more piece of information that is sort of available to us in this problem, and that actually is the percent ionization. So as we just saw on the previous slide, our percent ionization is equal to the H plus concentration divided by the initial acid's concentration times 100%. So what we know about percent ionization is they gave us the percent ionization. We do know the initial concentration of the acid. What that's going to allow us to do is actually calculate the concentration of H plus in the solution. So if we do that, and we rearrange that, the concentration of H plus will equal the percent ionization times the initial concentration of the acid divided by 100%. And that's going to give us here 0.47% times our 8 molar divided by our 100%. The percentages are obviously here in this case going to cancel out. We're going to end up with 0.47 times 8 divided by 100. Going to get us 0.0376. And that's going to equal the H plus concentration, right? So first off, any questions on that calculation there? Why is that going to be helpful to us? If we look at our ice table, we can see that at equilibrium, the H plus concentration equals X. And because it equals X, that value we just calculated is also that X, and it is also that X as well. So from the ice table, we can see that that basically is what X equals. And now that we're able to use the percent ionization to figure out really the H plus concentration, ultimately what X is, the change, we now can actually get values for everybody at equilibrium. So the concentration of our acid at equilibrium would be our 8 molar minus X, which is 0.0376. And that's going to give us 7.9624. We could also see that the H plus concentration will equal the HCOO minus, and that's going to equal, in this case, our X value, which is 0.0376 molar. At this point, we can now put all those numbers in, 0.0376, as that's equilibrium here, times 0.0376 divided by 7.9624. And if we do that, 0.0376 squared, basically, divided by 7.9624, going to give us a 1.8 times 10 to the minus 4 as our Ka value in this case. So this is one way that percent ionization can be sort of used to sort of backdoor sort of our calculation here. Obviously, you could just straight up calculate the percent ionization. So the percent ionization of an acid, again, is the amount of H plus that comes off from that acid that's freely floating in the solution. And by the way, if you did percent ionization of a base, it would be the amount of OH minus that came off of your base that's floating around basically in the solution at that point. Any questions on that one there? It's kind of similar to the equilibrium experiment where we kind of backdoored the calculation there by figuring out the X values. All right, so continuing on, we talked about weak acids. Obviously, weak bases are also involved. And weak bases, just like weak acids, will set up an equilibrium, which means, again, you will need to do sort of an ice table here to solve for the pH. Here we'll do our products over our reactants and adding to our growing list of K values. Since this is a weak base, this is a Kb value, B for base, and it's the ionization constant for a weak base. Much like acids, a strong base will not have a Kb value because, again, they will not set up an equilibrium. So if you see a Kb, again, you should know it is a weak base, and also that you should be doing probably an ice table to do your calculation. The ice table is going to work exactly like all the others. The only difference and where people oftentimes screw up on is when you do solve for X in this particular case, it is the hydroxide concentration. It is not the H plus concentration. So it's a very common mistake. People will do this and just automatically throw it into the pH, thinking they're calculating the pH, but really you're going to be calculating the POH here. So you got to go POH on these calculations and then subtract 14 and get yourself to the pH. So that's, again, a very common error as well. As we also, I think, talked about earlier on this chapter, when you're writing the equation, which you will have to do, again, including the water with the weak bases is a really good idea because, again, you can kind of just kind of visualize maybe where the hydroxide comes from, as that water is going to act as an acid in this particular case. Just like our Ka values, as the Kb value increases, so does the strength of the weak base. And it's really the same reason. Again, a higher K value, again, going to mean we have more products at equilibrium. Because we have more products at equilibrium, that would mean we have more OH minus in the solution freely floating around. And that would be a stronger weak base, obviously, in comparison of one weak base to another. Again, a strong base is going to be way stronger than any weak base, but in comparison of two weak bases, I could use the Kb value to kind of compare that. Any questions on that there? As that guy is yelling at you there, again, you're solving for the OH minus rather than the H plus in this particular case. All right, so here's the table in your book, which again, you may have to reference some Kb values. As I might have mentioned as well, a lot of weak bases are organic type bases, and organic molecules are basically carbons and hydrogens, and a lot of those guys will have nitrogens in them, and that's where you find a lot of sort of weak bases, or these organic sort of bases. So let's try one here. What is the pH of a 0.15 molar solution of C2H5NH2 if the Kb is 5.6 times 10 to the minus 4? Okay, so let's see how you're doing. So again, in this case, we got a Kb, which again tells us it's a weak base. And that means that we need a little dissociation reaction. So remember that, as I mentioned, with the weak bases, I would include the water with it. Again, just to kind of visualize maybe where it comes from. Since that is a weak base on the left there, the water is going to act as our acid and donate over our H plus to it. So we're just going to add on an H here. I'm going to just put it at the end. Remember, it's not just the H, but it is the plus, so it will become a plus charge there. And when water loses the H plus, it will be left with one hydrogen, one oxygen, become hydroxide, and hence here our base that is being formed in this case. That's going to give us our Kb, which is going to be our products here, our C2H5NH 3 and our OH minus divided by C2H5NH2. Again, like normal, we will leave water off as it's a liquid in this case. So doing our ice table here, we're going to go 0.15. Again, we know we need to do an ice table because it is weak. So minus x plus x plus x. Also, again, like normal, kind of ignoring water since it's not involved. So don't put any numbers there. Yeah. So we end up with something that looks like this. Any questions on that? We're going to go into our expression up there on top, going to give us x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. It is a small value of k, so you can't assume x is equal to 0. And again, if you check it, it's a very sad day today. That's a 6.1% here. Nothing good going on. So again, we're going to have to quadratic it. So we're going to multiply this to the other side. And that's going to get us an x squared is equal to 5.6 to the minus 4 times 0.15. 0.000084 minus 5.6 times 10 to the minus 4x. Bringing everybody to the same side, x squared plus 5.6 times 10 to the minus 4x minus 0.000084 equals 0. Again, our A, B, and C action there. Going into our quadratic, minus 5.6 times 10 to the minus 4 plus or minus. Again, if we do the inside of the square root, b squared minus 4 times a, which is 1, times c, which is negative 0.000084. It's going to get us a 0.00033631 inside the square root. And then if you square root it, gonna get you 0.0183, all divided by 2 here. Our 2x value is going to be, in this case, going the plus first here, 0.0183 divided by 2, x value of 0.00887 are most likely, again, a negative number, which is not going to be good for us in this case, and a negative 0.00943. Once again, negative not good because here we are looking for what x is equal to. That means that in this case, our x, which equals, a reminder, not the H plus concentration, but the OH minus concentration, will be this guy here. That again allows us to go into our POH first, minus the log of 0.00887. and that's going to go minus log 0.00887. That's a 2.05. And then our pH would be 14 minus that, 205. And if we do that, 1195 on our pH, which makes a lot more sense since it is a base, and that definitely is a basic pH in this case. So again, you can see hopefully it is really the same sort of calculation. Definitely want to always check the assumption, as we ran into several today that did not work, right? And obviously the other really important thing that people truly struggle with these is writing the equation and forgetting that it's actually OH minus. And sometimes that's related to each other because they write the equation and end up with H plus on the right-hand side instead of OH minus somehow. So you want to make sure you're doing those things correctly. Any questions on weak bases? Yeah. All right, so let's talk a little bit about some of these Ka values that we've been seeing. So we have a Ka value for our weak acids. We have a Kb value for our weak bases. And sometimes people are maybe not sure which one they should be using. So a really easy way to know which one you should be using, and this is all provided, obviously, you write the reactions correctly. If you see H plus or H3O plus on the product side, that is definitely a Ka situation. You should be using a Ka situation. If you write your equation, you see hydroxide on the product side, it definitely is a base and you should be using a Kb value. Now, if we actually add these two reactions together, our Ka and our Kb reactions together in this case, we will get a few things canceling out, and we basically be left with our good friend water, which also has a K value associated, which is Kw. And as you hopefully remember, right, when you add two these equilibrium reactions together, what do you do with the K value? You multiply them, right? So that gives you a really important relationship that if you take the Kw, it will equal the Ka times the Kb value. And why would you maybe need to use that? You will need to use that in a lot of situations that we'll come across, because there will be certain problems where you'll be given the Ka value and you need the Kb value and vice versa. There's a whole set of problems we're going to talk about here and right now, I think, where it's a very common thing. You're given like a Ka problem, but you need an actual Kb problem to do that. So you can use this relationship here. Again, the Kw reminder is that 1 times 10 to the minus 14 number, right? So that is, the same Kw that we used earlier on in this chapter. So importance of writing the reactions correctly and seeing either H3O plus or OH minus on the product side, again, will lead you to hopefully the right K value there. Any questions on that there? All right, we're going to come back to this here because I do want to talk about salts, which is what our lab is about next week, so you have an idea what's going on when we get there, hopefully. So we'll come back to this and talk about acid strength. So we're going to kind of skip ahead here and talk about salts to finish up on today. So again, that will hopefully set you up good for the lab next week, started on Tuesday. So salts, hopefully, as you know, is really a byproduct of a reaction of an acid plus a base. And that usually gives you two things, a salt and water, right? And a salt is really just an ionic compound. It is, in all intents purposes, the old spectator ions that are just hanging out there in the solution as a result of this double displacement reaction that's occurring. Now, salts can be important because they can, in certain cases, decide, I would like to continue to react. And they will continue to react with water in a reaction known as a hydrolysis reaction. So they have the ability to kind of continue to react with water. And because they can react with water, they will basically do one of two things, as we'll talk about. That salt can react with the water that's present. And frankly, it can take an H plus from the water and it can produce hydroxide as a result of that. And it can make the solution a basic solution because this reaction is basically going on. Alternative to that, the salt can donate an H plus over to water and produce H3O plus, which will then make the solution acidic. So these salts have the ability to react with water, which is present obviously in the solution, and kind of can continue to react and have a pretty good effect on the pH of that solution, depending on what type of salt you got going on. So how do you know whether or not a salt will sort of react with water or not react with water? This is where that relationship that we talked about earlier on when we were talking about Bronsted-Lowry is an important relationship to remember. And that relationship is this: if you have an acid, right? And I think I wrote it out like this. If you have an acid that is a strong acid, its conjugate base is going to be relatively weak. And if you have a weak acid, its conjugate base is going to be relatively strong. And the same thing happens for your base and the conjugate acid relationship. If you have a strong base, its conjugate partner is going to be relatively weak. And if you have a weak base, its conjugate partner is going to be relatively strong. So this is the situation with hydrolysis reactions and salts reacting where this comes into play. If you have a conjugate base or a salt that basically comes from anything that is strong, it will not go through hydrolysis, so it will not react with water. If you have a salt that basically came from a weak acid or a weak base, it will be relatively strong and it will go through this process and either produce OH minus or H3O plus. Any questions on that? So that relationship is really important to remember. And when you're dealing with salts, it's also really important to think about what acid and base it probably came from, right? What really kind of created it. And that will help you decide. Two questions really will help you decide: would you expect hydrolysis to occur? And if so, what's going to happen when it does occur? And so let's take a look at, first off, neutral salts. And neutral salts are salts that basically come from group 1 or group 2 on the periodic table. And if you remember, group 1 and group 2 on the periodic table is pretty much where we find our strong bases. And that means the conjugate partner from it is going to come from a strong base, which means it's not going to do much. Or it comes from a strong acid and it will not do much. So if we take a salt like sodium chloride, basically sodium chloride is a salt that when it is in solution, because it's a salt, it will completely break apart into a sodium ion and a chloride ion. So again, if we just kind of think about like where this salt probably came from, it most likely came from what acid? Hydrochloric acid and sodium hydroxide. Yeah, this is most likely the reaction that produced the salt in a double displacement move. Yeah, and there you go. You get your sodium chloride and your water, right? And that is, again, our salt and water in this case. So our salt most likely came from those two things. And since HCl is really where the Cl minus comes from, it is going to be relatively weak to Cl minus. And as I just mentioned a second ago, it will not go through hydrolysis. So you would expect it to actually be neutral, and the pH of that would be 7. Sodium here, ion, most likely came from sodium hydroxide, which is also a strong base, and it's group 1 and 2 from the periodic table, which is again where our strong bases come from, and we would not expect it to go through hydrolysis. So we would expect a solution of sodium chloride to basically be a neutral salt is considered, and the pH of that solution should be 7. Any questions on that? So again, if you look at your salt and it's like that, both parts probably came from a strong acid, strong base, you would expect that pH of that salt solution to be neutral and not go through hydrolysis. Any questions on that there? Now, let's say we took a salt like sodium acetate. And sodium acetate, which is a salt, will break apart into a sodium ion and a acetate ion. And in this particular case, if you had to maybe just think about where that sodium acetate probably came from, what acid do you think sodium acetate would most likely come from? What acid sounds like acetate? Acetic acid, yeah. So most likely the acid that was involved here was probably acetic acid. And probably our good friend sodium is going to be supplied by sodium hydroxide. And in this particular case, acetic acid is what type of acid? This is a weak acid. I know it's a weak acid because, frankly, it's not one of those six strong acids, right? So it's not on that list. So it is a weak acid. So when I look at the sodium, I know it most likely came from here and it's group 1 or 2 on the periodic table, which means I do not have to worry about sodium doing anything with water. But when I look at acetate, because it comes from this weak acid, it should be relatively strong and go through hydrolysis because it comes from a weak acid. So this guy is going to continue to react with water. Now, because it comes from this weak acid, I know acetate should be the conjugate base to acetic acid, right? And that's important because the reaction that's going to occur in this case is the acetate going to react with some water that's hanging there. And because I know this is really the conjugate base to that acid, I know exactly how it's going to react with water. What does a Bronsted base do? Donate or accept an H plus? A Bronsted base will accept an H plus. So because I know that that's going to be a conjugate base, it's going to act as a base when it reacts with water, and it's going to accept the H plus from water. It's going to act as a base down here, and water will act as an acid. And what's going to happen in this case is you will always form where it came from. So you will always form pretty much where that part of the salt came from, which is acetic acid, and it will form some hydroxide right now at this point. First off, any questions on that? Which, if you had to guess, this salt solution should be acidic, basic, or neutral. It formed hydroxide, which means it should be basic, yeah. So if you have a salt that comes from a weak acid, it will go through hydrolysis and it will act as a base with water, accept the H plus over and produce hydroxide. And you would expect the solution to be acidic. I'm sorry, to be basic in this case. Now, without doing a calculation, I know it's going to be basic, but if I was going to do a calculation at this point, this is our good friend, the ice table calculation. And we would do our molarity of our salt. We would do some zeros. This would be minus X, a little plus X action, right? This is going to be my initial concentration minus X, X, and X. This would go into my equilibrium expression, which would be, in this case, my acetic acid, my hydroxide, divided by my acetate in this case. This would be a K what? It would be a KB. And you know you should be using a KB. So a second ago, I told you there are problems where you will be given the wrong K value. This is the type of problem. If you had this problem and they asked you to calculate the pH of sodium acetate, they most likely will give you the Ka value for acetic acid. And that's where you can use that Kw equals Ka times Kb to calculate the Kb value for it. So hydrolysis problems here, which is what this is. This is referred to as a hydrolysis problem because we're reacting with water. Will always, and I would say most cases, you will have the wrong K value. You will need really the opposite one. And that's why it's, again, really important to be able to write these equations because, again, it's a very common error. People will go into this and use the Ka value that was given to them. And you want to make sure you do that. So again, that's why it's important to recognize that if you see on the product side, H3O plus or OH minus, you need to make sure you're using the right K value, the Ka or the Kb, depending on what you see there. Any questions on that? Obviously, to solve this, normal sort of ice table assumption, quadratic. Yeah. Yeah. So that's a value it would probably be given to you, but it's a value you use. So it's that 1 times 10 to minus 14 that we used previously. Yeah. Um, So let's then talk about another type of salt solution. So we have neutral solutions that come from strong acid and strong base, or group one or two on the periodic table. We have basic salt solutions that basically part of the salt derives from a weak acid. So we also, maybe no surprise, there's acidic salt solutions as well. And acidic salt solutions come from the opposite of what we just saw there. So if we had a salt like ammonium chloride in this case, and ammonium chloride will break apart into NH4 plus and Cl minus. So again, if we sort of think about each of these parts of the salt, and when you have a salt that's given to you, that's really what you want to kind of think about, which is, will any part of this salt continue on and do hydrolysis and react with water? And that's what you want to kind of look at. And you do want to look at both parts of the salt. So here again, we talked about this guy earlier. Most likely comes from HCl, right? And it's going to be a neutral salt. So we don't really have to worry about the chloride part of it. NH4 plus, as you perhaps might remember, most likely comes from our friend ammonia, right? Which is a weak base. And that is a strong acid. And that's basically how we make this. We make a little ammonium chloride, which you could either put together or separate like it is up there. That's basically how we get that. And because it comes from a weak base, this guy is going to go through hydrolysis. Again, anything that comes from a weak acid or a weak base is going to react with water, is going to go through this hydrolysis reaction. Again, understanding that this comes from a weak base, we will know that this is conjugate acid. And that is how it's going to react with water. So it's going to be NH4 plus going to react with water in this case. And because it's going to act as an acid in this case, it's going to donate the H plus over. The result of that is it will always, as I mentioned before, make where it is coming from. So it came from NH3, it will make it. And in this case, when that water accepts the H plus, it will form H3O plus. Now, people sometimes have a really hard time writing these equations. But again, if you kind of think about where it comes from and you look at the actual problem, there's a lot of information that can help you sort of figure out what goes on the other side. So, for example, without doing a calculation, this solution should definitely be acidic because we are producing H3O plus in this case. And we will also most likely be given in this case the Kb value for NH3. So if you have this salt, you most likely would be given the Kb value. So you would need to convert it into a Ka again when you do your calculation. Calculation again, like the previous one, is going to be an ice table where you're going to use your molarity and your zeros and your x's, basically, right? And again, this is going to go into a Ka. Difference here, though, when you do solve for x, it actually does equal the H plus concentration. So you could go right into the pH, as opposed to the previous one when you solve for x, is you can get the hydroxide concentration, going to go POH, and then into the pH in this case. So this is one way that you could have a salt that is going to be acidic. Another way that you can also sort of have an acidic salt is actually certain small metals that have high positive charges, like plus twos and so forth. A lot of transition metals and aluminum and stuff like that can also be considered a salt and do an acidic salt. And how that sort of goes is, we'll take a look here. Actually, I'll just use this to draw it. So if you had something like aluminum that maybe is surrounded by six waters, has a plus three charge, this guy basically is an aluminum ion that is attached to six waters, basically, with it. It is what we'll talk more about in a later chapter, really a complex ion. It is also really when you write this and you just put aqueous, that's basically what you got going on basically there. One, two, three, four, five. I'm going to show one attachment correctly here with the water. And by the way, the water would attach through the oxygen, which is more negative, with the aluminum being more positive. This entire thing has a +3 charge because of the aluminum. Each water is neutral, right? So that's where the +3 charge comes from. So what happens in this particular case is just a regular old water floating around will come by, and it will basically grab one of those hydrogens off of the water that's attached to the aluminum. And when it does that, that combination is going to form H3O plus hydronium, basically H3O plus. Yeah. And what happens with our sort of complex ion is we still have our, I'll go this way. We still have our aluminum, and we still have one, two, three, four, five intact waters that nothing happened to. But when this guy loses his hydrogen, he's left with OH, which is hydroxide, right? And we're left with hydroxide. Hydroxide is -1, and -1 and +3 gives you a +2 left over. You get this weird, funky looking thing, which in a later chapter you actually know how to name, but we'll talk about that in a later chapter. And you will produce, in this case, the H3O plus. So small metals that have positive charges, especially transition metals, +2s, +3s, they have the ability to kind of do this sort of hydrolysis reaction. And this is another way you can have sort of an acidic salt. Any questions on that there? Now, in each of these examples that we talked about, only one part of the salt went through hydrolysis, right? So either it was like this guy, the acetate, or it was the ammonium, and the other part didn't go through hydrolysis. It is possible that you could have a salt, for example, where maybe you have something like this, where if you take a look at this salt, which is ammonium nitrite, that is going to be the ammonium ion and the nitrite ion. Yeah. So this guy, as we talked about, definitely will go through hydrolysis, like we talked about with, because it comes from NH3, right? This guy most likely comes from what acid? Not nitric acid, but nitrous acid, yeah? And nitrous acid is a weak acid because it's not one of those six, right? That's on there. Its friend nitric, which is close to it, is, but this is not. Which means in this case, actually, both of these guys can actually go through hydrolysis. So it is possible that both parts of the salt can go through hydrolysis. To separately calculate what happens is very complicated. So what we typically do if you have this situation is you compare the Ka value to the Kb value. And whichever one is larger, so you compare the Ka value for your NH4 plus to the Kb value for NO2 minus, and whichever one is larger is what will most likely happen. So let's just say, for example, here the Kb value was larger. We would ignore the sort of Ka and just do the Kb calculation, or vice versa. If the Ka was larger, we would do just the Ka acid sort of calculation. Any questions?